Alright, so, volume of a solid of revolution using the disk method. Here we go. So we're going to do a little bit review at the beginning, and we're going to look at what we would do when we were approximating area under a curve from one particular value to another value. You remember? Let's say I draw some random curve. Okay? And I wanted to approximate the area under that curve from here, which was A, to here, which is B. And I wanted to do it using a, a left-handed Riemann sum. Yes? So we would draw rectangles, and we would use the left-hand side to figure out the height of that rectangle. And we're going to make them the width of the little marks already. Cool? You with me? Only go to B. Don't get excited like I did in the other block and I just kept going. Okay? So we have these rectangles, right? Now, are they exact? Will they give me the exact area under the curve? No, just an approximation, right? Seems to be an over approximation, right? Yes? Alright, then after we did that and we did the whole summation thing and we added up the area of each of those rectangles, right? We decided to draw more rectangles and draw more rectangles and more rectangles and more rectangles and more rectangles until we drew an infinite number of rectangles. And in order to do that, I have to make this delta x down here become what? Some number very, very close to what? To 0, so I have an infinite number of rectangles in there, and when I do that, I have the exact area under the curve, right? So in order to do that, we had to add what to the summation notation that we had? What do we have to add to the summation to make it draw an infinite number of rectangles?
Oh, infinity. Or
What? Had to take it to the what? Starts with an L. Take it to the limit, right? Right, remember we had that summation, and then we add the limit in the front of it? Yeah? And then all together we said that, oh, that whole thing was equivalent to the integral, right? Remember we did that whole sheet with a whole bunch of problems that you were matching?
Oh, yeah.
Yeah, it wasn't just for fun, right? It was to make the connection. Anyways. Alright, so this is technically, if we wanted the exact area, right, we would say the integral from a to b, we're going to call this function f of x. F of x dx, right? That's what we would do to calculate the area? If I wanted the exact one? Yeah? Alright, so I want you to imagine having those rectangles, okay? And if I were to revolve this curve about the x-axis, it would create a three-dimensional figure. And I want you to imagine those rectangles also revolving around the x-axis. And if they revolved around the x-axis, what shape would they form? They would form a cylinder, right? Which we call here a disk. Okay, and the reason we're calling it a disk is because we want that height of that cylinder to get what? We want that height, right? That height, do you see the height? If I were to get this disk and turn it over, the height would be the same as that delta x, which we wanted over here to get what? Closer and closer to 0, so that way I could have more and more what? Disks, not really cylinders, right? Because the height of those cylinders is going to become so small that there's going to be really tiny, right? So they're going to just be like little what? Little disks. You understand? That's why they call it the disk method. But yes, it would be a cylinder. So I got that rectangle and I rotated it around. And he created this cylindrical shape that we call a disk. Yes? And if I have an infinite number of those disks, and I find the volume of each one, and I add them all up, that would be the same as the volume of the shape that is created by what? by revolving that curve about the axis, or about whatever axis you want.
Is that like the pens?
Like the pens, right? This is exactly what we're gonna do on the pens. So you're gonna create your pen, then you're gonna put it along the axis, and you're gonna find some points. And you're gonna use those points to come up with a regression model, like a quartic or a quintic regression model. And then you're gonna use that equation, and you're gonna revolve it. And as you revolve it, it's gonna form the shape of your pen, right? And then you're gonna find the volume that is created by that. And we're gonna do it using discs. We're gonna assume that it's solid, that there's not a hole in the middle of the pen. But yeah. Cool? That's the whole point of the pen project when we get to it. Alright? So anyways, do we understand? Do we see that we're creating those cylinders? What would the radius of the cylinder match with when I look at the rectangle? The height, right? So the height, that f of x, would be the same as the radius of that cylinder. Yes? The height of the cylinder, which is the width of the rectangle, is like the delta x. It's going to be represented by this dx part. You want to visualize it? I have a really cool app on the computer that shows it. It's really neat. Let me show you, so maybe you'll get a better idea.
Would you say yours something? So your what is this one? Care Bear. What's that Care Bear? I'm Care Bear. What is that? Care Bear. You know? What's that Care Bear?
It's a long password.
The red one.
Hopefully nobody figures it out. Alright, so there it is. You see it?
Yes, I see.
Let me see if I can refresh it, 'cause it's missing something. There it is. Alright, so I'm going to show you a single disc. Okay? What it's going to do is it's going to draw the rectangle over here. You're going to see the rectangle being drawn over here in the three-dimensional. Ready? There's the rectangle, which is technically, the height of it is the radius, right? Here they're doing a right-handed Riemann. See it? Okay, that's the area, right?
Whoa.
Cool? Alright, so now we're going to revolve it about the x-axis, right? Here it goes. You can see it revolving. And it forms that cylinder, or that particular disc.
Are they ever gonna tell us to find half of it, or like 1/4 of it, or something like that?
I mean, they're going to give you a restriction, like to find the volume from a particular number to a particular number. And that's what's going to go in your interval. Cool?
Yeah.
So let me show you the different rectangles with the different discs. Right? So here I have two discs, right? So we have, see that? Ooh. Cool? Thought that was super awesome. More discs?
Yes.
The more discs I have, right, the thinner they get, the better the approximation of the volume. So if I do one, that's not pretty good, right? So there's two, there's three. And it starts to take the form of the three-dimensional shape, right? Ooh, like a 3D printer,
Put
right?
20, put 20. Oh, 50.
So there's
Wow.
50, right?
I've practically.
Spin it. You can't see them because they're so little. It just looks like a line, right? Pretty cool? Wow. Let's make it less. Like right there?
Better than you?
Is that too many? Let's see. Pretty cool? You understand?
Probably can't.
So what we have to do is we have to find the volume of every single one of those discs, right? And we need to add them up, right? So that's where the integral formula comes into play. Because the integral is a summation, right? That's what the S stands for in the integral. That's simple, right? Now each one of these has a different what? Each cylinder has a different what? A different height, right? A different radius, right? So that radius that the formula that we're going to use to figure out that radius is going to be the what? The curve, right? At every single point. So it's going to be the curve, which is the top function, minus the axis, which is the bottom function, that's gonna give us the radius at every single point in between whatever interval I want. Okay, now we're gonna need a formula to find the area, the volume of each one of those discs, which you said was a cylinder, right? Yeah?
Grab my.
So,
Do it.
let's see if we can draw one here.
Tell them I'm really good.
I'm not really good at drawing three-dimensional stuff, but let's give it a try. Yeah? I don't know, let's try to make like a bowl or something.
If it was me.
That's already better. So then if I reflect it, I think it's gonna be like, starts here and then goes down. And goes like this. Yeah, does that look like a good reflection? Sort of?
I look like a base.
So we're revolving it about the x-axis, right? We're revolving this curve. Let's try to create the three-dimensional view.
You did that so fast.
Wait, what the hell are you? What's going on?
What?
Judith, help us, Judith. Judith, don't laugh at me. Well, now I got confused. Am I going this way or this way?
Oh.
I don't know what I'm doing. Making this up. Okay? I never
You're
took
making
art.
this up as you go.
I just took it in middle school. How does this look, Luis? Okay? You're a pretty good artist.
Why I should sing.
You didn't do it. So I don't have too many discs here, right? But if I add more discs, the more discs I add, the better it is. Pretty cool? Yeah? And this is the stuff that they need to be able to enter into a machine, right? That creates the objects, like for candies, right? There's certain candies, like a Hershey's Kiss, right? Yeah, that's a solid chocolate. So they need to be able to enter a formula in there that's gonna create that shape, right? Or they need to put in a formula that's gonna create the mold that's gonna make that shape, right?
Saying they use calculus.
So calculus is everywhere, you just don't realize it. Pretty good? Alright, so what's the 3D shape that we know how to find the volume of that matches this disc? What do we say it was called? A cylinder, okay? And what was the formula for the volume of a cylinder?
What's that? You
Big base times height? No, area of the base times the height. So pi r squared h. Okay? H is going to be the same thing as the delta x, okay? Which we're going to reference as just dx, because that's going to get infinitely small. The radius, we said we had to calculate it, right? The radius is going to be from the axis to the curve, right? And that's going to change. So to find the radius, you're going to have to know whether I'm doing top minus bottom or right minus left, depending on what axis I'm rotating about. Okay? I think this was on the mock test. So, really quick, the formula is super easy. Okay? The only thing that we changed is we add the integral in there. So that way you can add up all of those volumes really quickly. Pi is a constant, so that's not changing. The radius is changing at each different place. Okay? So it's going to be pi times the integral from a to b of the radius squared times dx or dy, depending on what you're revolving around. If you're revolving around that vertical axis, it's dy. A horizontal one, it's dx. Okay? Now how do we figure out the equation that goes in here for the radius? It depends on what's happening. Top curve minus bottom curve, or right curve minus left curve, depending on what we're revolving around. Got it?
Got it.
Seems easy? You think you can remember that formula? Because you're going to need to know it. It won't be on the formula chart. Oh wait, there isn't a formula chart on the AP chart.
What's the formula chart?
Okay? It is on those handouts that I gave you though, okay? So let's write it down. Okay? So we said it was pi times the integral from a to b of the radius squared dx or dy depending on what I'm rotating about. Now this is only for volumes by disks. This is for volumes of shapes that are solid, that don't have a gap in between. Okay, these are gonna be entirely connected to the axis that they're rotating about. Okay, if you have a piece of a graph that's not connected and it's rotating, then it's gonna have a gap there. Do you understand? So like, let's say this is the axis, and I have this line and I'm rotating it about here, then this space right here is gonna be filled in. It's gonna be solid, but it's gonna have a space here that's gonna be what? Empty. Okay, so then it's gonna change. Sort of, kind of, maybe?
Yeah.
Not really? Alright. But if I revolved it around this guy, then there wouldn't be a problem, right? Yes or no? Maybe? We'll talk about those later. Those are gonna be washer problems. Okay, because washer is like a cylinder, but it has a what in the middle? A hole, so it's like you're creating two cylinders. A big cylinder and then small cylinders inside. So you gotta get the big cylinder, which is everything minus all the little cylinders inside. Cool? Sure. Alright, so let's give this bad boy here a try. Find the volume of the solid form by rotating the square root of x about the x-axis from 0 to 4. Let's see what we got. We have a little bit of time, maybe we can get through one. Alright, so